So, hi everyone, I'm Alice. I'm presenting on sea ice models, but I want to emphasize that a lot of what I'm talking about is done by other people in the Polar Climate Working Group in general, which is, as part of the Community Earth System model, how we do development. We work with people at different labs or universities, and so there's a lot of people who contribute to the actual model development here. All right, so a little outline of what I'm going to talk about today. I know we've talked a lot, I'm on the last day, about different models, but just it seems like we all come from different backgrounds. So I'm going to talk a little bit about CS models, what they include, before I start jumping into some of these improving model processes, and I'll talk about some stuff we're doing kind of right now that will be in the next version of CESM, and also some future work that we're interested in before closing. So the first thing about sea ice, this should surprise no one in this room, but when you have sea ice cover, we have a surface that is very heterogeneous. So we have, as you can see in these different, let's see if I can, okay, cool. All right, so we have ridges, sometimes we have leads. This picture is showing melt ponds. And the main thing is you can tell that these surfaces have a lot of that heterogeneity. So we need to be able to represent all these different impacts on the surface within a sea ice model. It's also a little complicated on the land when there's snow or something like that. It just stays put. The sea ice moves, so you have to keep track of it and these different surface conditions as it moves around. So we have tracers. And then we have different flows of various sizes. Another thing that makes sea ice kind of complicated is that if you're in the Arctic versus the Antarctic, the dominant processes may be different, but we're looking at global models, and so we want to be able to use the same processes in the sea ice in both hemispheres. So it's not like we're turning some processes on in the Arctic and not in the Antarctic. We want the system to be fully consistent. So like in the Arctic, for example, melt ponds are really important as part of the seasonal evolution, whereas in the Antarctic, they really aren't, but snow ice formation, for example, is. So we want to be able to represent both of those types of things. One thing I just wanted to bring up, I've heard a number of people talk about ensembles and looking at stuff. So one question that we often ask is, how do you know if a process actually matters? And what I'm showing here is the CESM2 large ensemble. So this is 50 different iterations of the climate model. It's the same model code, the same forcing. We just start the atmospheric conditions in 1850 with a round-off level perturbation to the atmospheric temperatures, and then you let the model freely evolve. And so you can see there's a wide range of possible conditions. And these are the observations from the National Snow and Ice Data Center. And you can see that they're kind of on the upper end of what CESM2 was able to resolve. So we just tuned one little parameter in the snow grain radius. And one thing I want to point out, there's only 4 ensembles here, but this is the light blue. Now you can see that we really do have all 4 of these ensembles are above most of the envelope of the CESM2 large ensemble. So we really are having a climate difference. Tuning this snow grain related parameter does impact the sea ice mean state. Does that always happen? No. So in contrast, this is a different simulation I ran where we smoothed the surface of the sea ice to see how that might affect momentum fluxes. To be perfectly honest, we thought we would see an impact, and as you can see here, the CESM2 large ensemble, that's kind of the gray here, and then this dark blue, this smoothed ensemble, it's right in the middle. So it did absolutely nothing to that sea ice mean state in a statistically significant way. I do want to emphasize that while this is the sea ice area, there are other impacts, so it did impact the sea ice speed. So depending on what science question you're interested in, there might be processes that impact the ice in different ways that you do want to resolve. All right, so what do you need in a sea ice model? So as I said, the first thing is we need a sea ice model that reasonably replicates the mean state and variability of observed sea ice. So that in general is concentration, thickness, mass budget, stuff like that. But we need it to do it in both hemispheres. You really want to have realistic exchanges of heat and moisture. We want it to respond to climate perturbations the way you expect. If we're going to increase CO2, you want to see that the sea ice might go away. And the other thing that's really important is we want it to be computationally efficient. So at least in these global or system models, we run for thousands of years, or we have many ensembles. And so it's really important that the code is actually efficient while doing this. So some of the sea ice models, everyone may be familiar with these, but I'm just making sure we're on the same page here, is that The model I'm most familiar with is SICE. This is developed now by the SICE Consortium. It's a group of international partners. It used to be primarily developed at Los Alamos National Lab. IcePack, which you may have heard of, is the 1D column physics that's used in SICE. So SICE is both the dynamics and the 1D column physics thermodynamics. And you can get all this code online here. It's bolded because that's the model I'm familiar with. So I'm going to talk about process and development with SICE and CESM specifically. There are other models, of course. There's SI cubed or SI3, I don't know how you're supposed to say it, or SIS2. I'm not trying to make any value judgments on if these are good or bad. I'll just primarily talk about this because I know it well. And maybe during the discussion, people who know the other ones better can weigh in if there's important things to contrast. So another thing that we have with the sea ice models that are in pretty much all Earth system models is three main components. So the first component here is we have a dynamics component. So this is a well-known expression from the 1970s where we look at how there's a force balance between the Coriolis force, air, ocean stresses, the sea surface slope, and then internal ice stress. And by solving this force balance, we can figure out where the ice is moving and how it would deform if you get convergence or something like that. So that's like ridges you see here. So pretty much every Earth system model is going to have, or I think every Earth system model that's like in CMIP will have dynamics. We also have a thermodynamic component. So this is kind of the 1D IcePack part of the code I was talking about. So we solve for vertical and lateral melt and growth rates. And at least how we do this in CESM is we break the ice, regardless of thickness, into 8 different layers. And then we have snow on top that's broken into 3 layers. And you solve for a top surface flux balance, a bottom surface flux balance, and then vertical heat transfer or conduction through the ice. And within CESM, and I think many models now, we actually solve prognostically for temperature and salinity profiles. So we're using a mushy layer thermodynamics. This assumes that the brine channels and pockets are in thermal equilibrium with the rest of the ice. We have a salinity-dependent freezing temperature, and then the heat capacity and conductivity are functions of the ice temperature and salinity. But one thing I want to point out when, based on discussions that have come up here, is that we assume in SICE that there's non-varying ice and snow densities. I should have said snow here too. So the density is always 917 kilograms per meter cubed for ice and 330 kilograms per meter cubed for snow. And obviously that's not how it is in the real world, but that's how we do it in this model. The last thing that I think pretty much all CMIP style models have now is an ice thickness distribution. And this is really important, and I think this came up yesterday in some of the conversations, but this is a sub-grid scale parameterization. So within each grid scale, we know that there's ice of all sorts of different thicknesses. So that's what you're seeing here. This is like a cross section, but you have some really, really thick ice, and then you have thinner ice. And so we have a probability density function that describes the distribution of ice within each grid cell. And so what that kind of looks like, if you might want to imagine it, is that we usually use 5 ice thickness categories. There have been tests about this. If you get too many, it gets very expensive, and you're not really getting as much return for your buck. So this is a good way to kind of get some of this thickness distribution while still making it computationally efficient. So we have these 5 ice thickness categories, thick ice through very thin ice. We compute fluxes, so conductivity, albedo, et cetera, on each of these ice types, and then we merge those based on the fractional area of each of the types of ice. We also keep track of tracers, so this is like a melt pond and this is snow, for each one of those thickness categories. So for example, with albedo, we have our 5 thickness categories. Each one of those can have 3 surface types, which would be bare ice, snow-covered ice, or ponded ice. And so when we're calculating albedo in a grid cell, we actually calculate 15 albedos for all those different types, and then we merge those for like a grid cell average, and that is how we help get fluxes back to the atmosphere. But we really are looking at a subgrid scale thing. So when you look at model output, a lot of times all of these different ice types, that data won't be output because it's just costs way too much to store this. So if you're looking at CMIP data, maybe there's just one albedo, or you're looking at a net surface shortwave flux upward. But within the model itself, we're actually doing a lot of this subgrid scale calculations. And the ice thickness distribution changes over time. So we have an equation describing this distribution. You can see here an example of this where there's a high probability of ice, or there's a lot of open water, and then a decent amount of first-year ice, and then more multi-year ice, but much less very, very thick ice. And this can change based on thermodynamic growth, lateral melt, convergence, or redistribution. And an example of this, so you can imagine if you had convergence within a cell, what you're going to do is lose your probability here of open water or very thin ice, and then you're going to gain some thickness in these thicker categories as the ice converges, and you're getting thicker ice due to that. So mass is, of course, conserved. Area is not, because you could have a cell that you have convergence and an area wouldn't be conserved. You can also have a change in your PDF if you have thermodynamic growth. So you imagine you had your original ice flow here in cyan, and then you grow ice in this purpley color. You're going to gain probability in like the very thin ice as this open water freezes, but then in some of this thinner ice and a little bit in the thicker ice as well. The thicker ice grows less rapidly because of conduction is not as strong there, and so you get more probability here than in the very thick categories. All right, so hopefully everybody kind of feels like they understand what a sea ice model is and how it works. So I'm going to talk a little bit about some of the ongoing work that we're doing and future work to improve some of the processes that are in the model. So before I go, so the four that I'll kind of highlight for ongoing work, and these we're hoping to be in CESM 3, which is imminently going to be released. That's how modeling works. It's a little bit past where we thought we'd be releasing it. But so melt ponds, a flow size distribution, snow, and then how we're kind of improving satellite comparisons. All right, so melt ponds. People have talked about this a lot yesterday. Ellen talked about this. Ponds are really important in the sea ice for albedo. And at least in the model right now, they're only influencing radiation. So we're not looking at differences in conduction through melt ponds or anything like that, how they're affecting that. They evolve over time in the model, and they're carried as tracers on each of those ice categories, as I mentioned. And the parameterization does take into account if the sea ice is deformed or not. So if you have ridges or if it's flat ice, the ponds will form a little bit differently. So this is a picture of reality. Here's a pond fraction map that you can see for August, and you can see that there's high pond fractions kind of on the margins and then lower pond fractions towards the central Arctic. And that's a grid cell mean. So one of the opportunities we have here is that there are new observations. So the Mosaic cruise, which happened in 2020 and 2021, provided more observations of the seasonal cycle of albedo change. So that's shown in blue, and the Sheba observations from the 90s are in red. And you can see they're pretty similar in terms of the albedo evolution. And what we're seeing in the model is that the albedo evolves pretty similarly. So great, we're doing everything well in the model, right? No further work needs to be done. Well, as we dug deeper into the model, what we found was that actually the model's not doing this very well. This is now the ponded fraction of ice, and the observations from Sheba are in red and Mosaic in blue, and you can see that there's kind of a maximum pond fraction of somewhere between 20 and 30% here. And the model, in these kind of shaded blue and red colors, is getting up to like 40 or 50%. So we have way too much coverage by ponds. They're way too extensive. And similarly, when we look at the ponds themselves and we look at the albedo of the ponds in the subgrid scale way, you can see that in the model, this blue, the albedo is too high compared to observations. So that suggests the ponds are too thin. So these biases cancel out and give us a great albedo, great for the climate, not so great for the actual process representation. So David Clement-Stool, who some of you guys may know, has been working on a new parameterization of melt ponds. So this is the existing parameterization where ponds are kind of perched on the ice and they decay, but when they drain, it only reduces depth, it doesn't reduce area, and so they're too thin and too extensive. He's been working on this sea level ponds that will be in CESM 3, where the ponded area is no longer like perched above the ocean surface, but you have a pressure head, and when they drain, it will affect both the depth and the area and should be more realistic. So this is an example tested with an ice pack, again, that 1D column model against the Mosaic observations where these sea level ponds, so the solid lines instead of dashed lines, are more realistic in terms of the area fraction compared to Mosaic instead of growing continuously. And then this is looking at differences in first year and the transect ice. So some of the challenges here is that this is very much a process scale type observation from Mosaic. I think that an opportunity, but another challenge is to validate this new parameterization with things like Ellen is maybe doing new data sets from satellites to understand maybe how these sorts of processes change in time and look at how the model is doing in more of a statistical sense. We've also talked about the melt pond parameterization is still just a 1D part of the model, but there might be like 2D processes going on where ponds merge or there's, you know, horizontal drainage, stuff like that. And then, as I mentioned, the melt ponds are only affecting albedo right now, but they might have other impacts that are valuable to include. All right, another thing that we are working on right now is including what's called a flow size distribution in addition to the ice thickness distribution. So there's a new parameterization by Letty Roach that's been in IcePack for a couple years, but it hasn't yet been implemented in any global Earth system models. In addition, there's some new satellite observations. So I think there was a poster about looking and categorizing ice flow distributions, and this is kind of an open question that I'll get back to in a minute. But when we look at pictures like here from IceBridge or from a satellite, you can just see that there are flows of like here's a big flow and then there's smaller flows, and you can see that here as well. And in general, we expect that the pack ice should have bigger flows and the marginal ice zone will have more little flows, and then as you get to open ocean, like there might be a couple flows in here. And the flow size matters in terms of the melt around the outside of the flow in particular. And in CESM2 and previously, before this flow size distribution, we just assumed that all flows had a constant diameter of 300 meters. So that's not necessarily very accurate, and it doesn't necessarily represent transitions between, say, the pack ice and the marginal ice zone. So this is the equation for the joint flow size and thickness distribution. The flows, you know, sea ice that forms in wavy conditions, if there's wind and stuff like that, are more likely to be rounded. So this is like traditional Antarctic ice where you have pancakes, whereas if it's very quiescent, you'll get like nice nihilist ice forming and stuff like that. So we want to be able to represent some of these differences. So there are thermodynamic terms in this equation where you can have flow growth or melt that's due to the lateral size. Of course, there's advection, and then there's also mechanical interactions like flows coming together and then welding, or flows that are on a wave and there's too much stress on either side, and so they break and they're going to get smaller. And so we have we've implemented this in CESM3. There were some hiccups along the way in terms of like the cost. It was really expensive, so we're trying to figure out how to make it less expensive. I think we've gotten past that, but you can see that it roughly seems to be doing what we expect in terms of our intuition, where the interior pack of the Arctic has very large representative radii, and then as you get towards the marginal ice zone, the radii get smaller. This is what we're seeing in the Antarctic as well. And this is kind of an older version where we're talking about tuning it, so these things might be changed a little bit, but this emphasizes some of the challenges that we find. So one, I mentioned it's expensive. Two, there's questions about what observational baselines should we use to evaluate this. I think there's a meeting at the end of next week, or maybe it's the end of this week. There's a meeting about this to talk about waves and flows. I think it's at Brown that's coming up to discuss some of these questions. And then this is still really new. We haven't run it in big, long climate simulations, and so we don't really know what the impacts are on the climate mean state or the variability. And we don't have a lot of intuition for how to tune this or if it's behaving well. On the other hand, it allows new and interesting science questions like, you know, does flow size change a lot during a storm, and will that impact, say, you know, some of the snow processes or predictability or melt, those sorts of questions that I think people are interested in looking at but haven't been able to look at up till now. All right. Another process that we're investigating, snow. So Ethan talked about this as well. Snow is really important for sea ice. Again, opportunity, there are some new parameterizations that have been added into SICE and not necessarily used before. And there are more of these new in situ observations like Mosaic as well that have looked at like how snow is lost to leaves or how snow is redistributed. So So one of the things that we are including, there's a snow redistribution parameterization in SICE. It includes things like compaction by wind or loss to leads. So we will be including this. There's also some new snow physics related to like snow grain radius evolution, the metamorphoses, all these sorts of things that impact albedo. So these are available within the model. We are not actually using them, at least for CESM, because it wasn't behaving as we expected exactly. And so I think there needs to be more development understanding about what's going on here. And then as I mentioned before, we still assume that snow is a constant density, which of course is not actually what happens when you have snow metamorphism. So there are things like that that people are interested in understanding, how that affects conduction, how that might affect things like satellite retrievals, being able to understand that whole process better. And then another one I want to talk about that's kind of in process right now is doing better satellite comparisons. So we have our models here, and what they actually calculate is thickness. So we know the thickness exactly, we know the snow thickness on the sea ice exactly. We know densities and the snow thicknesses, those are constant. But how we've usually compared the model output to observations is by using some observations where, say, ISAT2 or CrowdSat actually measure freeboard, and it's either the atmosphere snow interface or the snow ice interface. And then assumptions are made about the densities and the snow thicknesses that introduce uncertainties, but then we get a derived thickness. So in the past, we've kind of compared these two outputs. Another thing we're looking at comparing more directly is the actual measured freeboard and the derived freeboard, which you can do exactly in a model because we know the snow and ice thicknesses and densities, and so you could have a better apples to apples comparison here. And so Alec Petty and others are doing this. It's done after the model has been run, so it's not at the same time. But here's a mean state of the freeboard on an annual basis. And then he's done some work to compare the different models, translating their thicknesses into freeboard and looking at if they're reasonable or not. So I'm just showing the Arctic here. Many of the models have pretty reasonable freeboards in the Arctic. It's a different story in the Antarctic. And I think that has to do some with understanding what's happening with the snow there. So the opportunity here, there are some new data sets. There are long observations now from ISAT2, so we can look more at a climate timescale as well. And it allows this more apples to apples comparison. I think one of the challenges is this communication across communities. So different communities, of course, use different products, and you just need to make sure that you're talking about what you're doing and that you're using the same products and you're doing this intelligently. And it sounds so simple, but communication actually can be really hard and cause problems. And then, as I've mentioned before several times, I think, especially in this observational sense, density and snow thickness are big challenges in knowing what like the ice thickness is. And if models can help inform that, or we can test different ways that these assumptions are done, I think that might be valuable for better understanding the observations as well. All right, so that was all kind of ongoing work. I'm going to talk a little bit about future work that, we're not doing necessarily right this second, but we hope to do either in the next year or, I don't know, maybe more 3 to 5 year or longer time frame. So I'll first talk about conductivity through the ice, a little bit about biogeochemistry, and then these are not exactly ice processes, but impacts of high resolution or ocean sea ice, ice shelf coupling on sea ice that I think might become relevant in the future. All right, so conductivity. We've been working, so Lorenzo Zampieri, who was a postdoc at NCAR and is now at, I think he's at ESMWF. Anyway, he was using mosaic observations to understand why we have temperature biases in models. And so he was able to use these new observations and machine learning to develop a neural network model that links the predictors, which are like some atmospheric, some sea ice predictors, to understand the biases that are going on within our sea ice models. And what he found is that snow and ice heterogeneity on like meter to 10 meter scales, so much smaller than our grid cells, leads to a horizontal conduction within the ice, and that can result in a negative bias in the net upward heat, conductive heat flux, and that ends up leading to cold biases in some models. And so one of the suggestions is you can use machine learning to kind of tune your models and your conductive heat fluxes to be able to better match observations. I think one challenge with that is to make sure that if you're doing that, that the tuning stays within like what is physical in the real world. And if it can't do that, that tells you there's something else within your model that maybe needs to be resolved. So in this case, maybe we need to better resolve horizontal conduction or the heterogeneity and snow depth that would lead to that. And again, the conductive fluxes depend on density, and we are just assuming constant densities, and so that could be another factor that is influencing these. Something I've been thinking a lot more about recently is biogeochemistry. So there's pelagic biogeochemistry in the ocean, and then there's also biogeochemistry within the ice. Within CESM, at least right now, those are not coupled. But I think it would be interesting to do this, and we've been investigating the biogeochemistry, at least in the ocean, within these ice-covered waters. And we found some really interesting results where, like, the time of when you get a productive bloom is changing from now until the future, and you can imagine the sea ice is retreating, so that's part of why. But we're really missing this in the ice part of the productivity. We're also looking at how productivity changes under different categories of sea ice. So again, in this subgrid scale way, we're able to look at light penetration and look at what fraction of NPP is produced under different categories of ice and how that is changing in time. So you can see that at least in the Arctic, there's actually pretty equal amounts of production under the very thin ice in the next thickest category, but there's not under the very thick ice, and that's going away mainly because the thick ice is going away. And being able to understand this, again, with the actual biology that happens within the ice is valuable. So I think that there's an opportunity here in terms of developing processes and potentially feedbacks between the ecosystem and the physical system that we don't include right now. Again, these are new communities. I think there's a lot of applications and like impacts that this could be valuable for, fishing and conservation and things like that. Again, challenges, communication with new communities is it takes a while to develop these relationships. And then you need funding to actually do that, and it can take a long time for all of that to happen. Another thing I just want to mention is that there's a push towards higher and higher resolution. So I'm showing here the E3SM Earth system model, their grid. And the main thing I want to point out is that they have very high resolution in the Arctic. It's 10-kilometer grid cells or less. CESM has some configurations like this as well. And as we go to higher resolution, I think we're going to find that there are other processes that we haven't really thought about before that may be valuable and important to understand. So like eddies and how they're impacting the sea ice. When you get fast ice, how it's going to ground, and if there's a probability for doing that. Again, maybe it's probabilistic in different grid cells with the bathymetry. There's a lot of interest in high resolution for different applications. And then I believe it's fairly important to have a higher resolution to understand coupling to ice shelves. And this is more from the ocean side than the sea ice side. But things like this are going to be valuable for doing that coupling. Challenges when you start to go to high resolution, data management, both running it, storing the data, actually using it, it's really hard. Another thing I didn't mention here, this is high spatial resolution, but we've also found that daily resolution and output can be really important for understanding change. So monthly output is not always at the point we want. And then we don't actually include scale assumptions about, say, flow size or ponding. And what if we get to a size where we have a grid cell that's like approaching the size of a flow, or ponds might need to, span 2 grid cells? We don't know anything about that. And then the last thing here about future things is just this ocean sea ice sheet coupling. We're working on this in CESM. It'll be kind of a focus after CESM 3. Again, maybe not directly processes to sea ice, but the way that the ice shelves evolve and provide freshwater may affect our sea ice mean state. So I think that'll be interesting. So just the closing thoughts here. As I mentioned, we have a lot of different processes. I think when you decide what processes you want to spend time developing, you want to think about what the purpose is, like what actually matters. Will it affect the climate? Or if you care about forecasting, maybe you do care about ice roughness, even if that doesn't affect the climate. Comparing observations and models is actually, you want to be really careful doing this and make sure that if you have process scale observations, like from Mosaic, you're comparing them in a sensible way versus climate observations, so that a climate model is never going to exactly reproduce like 1 year of data. And I think the models can also help us guide different measurements we might want to take in the future where we know we have uncertainties or sensitivities. One of the things that I mentioned, we need multiple ensembles and higher resolution. This is expensive. I think there could be an opportunity in the future for machine learning emulators. So not that we want to get rid of dynamical models, but is there a way that we can use machine learning to help understand this physical system in a different way that makes it more computationally reasonable? And then the coordination across communities is a regular challenge. You need time and consistent funding for communication and 3-year grant cycles. And right now, who knows what's happening with a lot of the different grant sources is not always sufficient for doing that. So that's it. This is a figure I made of a sea ice party that ChatGPT created. Looks fun until you look closer, but I think it's kind of funny. So yeah, that's it.
All right, questions? Use the mics. Any questions?
Oh boy.
Earl, you got up there first, so I'll call you out.
Sure. Thank you for this really amazing summary. I guess the main question I have is following up on the sort of push towards high resolution. So a lot of the sort of rheology that goes into these models are continuum mechanics. Yeah. But as you get to 10-kilometer scale, that kind of assumption starts to get a little bit questionable. Are you thinking about revisiting how you parameterize deformation and things like that at those high resolutions?
Yes. So I wouldn't say that's not the top thing that we're doing right now, but I know like Andrew Roberts, for example, has a new scheme of doing deformation and ridging and stuff like that. So people are looking into it. I think that's kind of on the longer time scale. I don't think that's in the 3-year time scale, but it definitely needs to be investigated, and people are doing it. I would say I'm less of a dynamicist, so I haven't been doing that directly myself. But you're right that sort of stuff is really important to assess.
Thanks.
Yeah.
Yeah, thanks a lot. So the joint flow size and ice thickness distribution, I suppose that just as the ice thickness distribution has to assume some boundaries, and I was wondering whether you experimented a bit on the boundaries of the flow size in the model, whether the model outcomes is sensitive to that, in particular the maps that you showed.
Yeah, so we've been testing it and trying different parameters and trying to see what the impacts are. And like I said, since it's pretty new within this fully coupled sense, we don't have a lot of intuition yet. And Letty Roach, who I mentioned there, she's really the one who's been leading and testing and doing a lot of the analysis on it. So I believe she's tested some of those, but I don't know exactly which parameters and what's sensitive. It's more like she's giving us guidance for what she thinks is reasonable within the model. And I know that they're also, there's been development in different wave fracture schemes as well, and so that's part of it too. Like there was an older one, and she's been working on a newer one and things like that.
Thanks, Alice. This is a really informative talk. I'm curious about ocean sea ice interactions and what you see as on the horizon or big challenges when it comes to thermodynamic and momentum coupling, brine release, that sort of things.
Yeah, so one of the things that I think in terms of the ocean ice specifically is the sea ice right now floats on top of the sea ice. It doesn't actually depress the ocean at all. And so we don't have as good keel drag relationships and stuff like that. And I think that could be valuable to understand as well. This is biased by what we're investing in, I suppose, but I think this wave-ice interaction and understanding how that affects the growth and the melt and all of those processes is one of the big things with oceans as well. And when you get a storm, are we getting mixing in the ocean? Do we get changes in the flow size that could allow heat to come up, like some people have suggested during some of the cyclones in the Arctic? I guess that's kind of where I'm thinking some of those processes will be. I will be perfectly honest that I know that the ocean, at least in the past in CESM, is too stratified and doesn't have enough resolution near the surface to sometimes get these mixing events. And so I think before we get as good of those sorts of interactions, we need to make sure that the ocean is is responding properly there. And so I think hopefully in CESM3 we have a new ocean model. Hopefully some of that stuff will be better resolved, but we still have to do a lot of assessment once it's actually finalized.
Hi, Alice. Thanks for the great talk. So you mentioned the melt ponds in the model only impact the radiation. Mm-hmm. Does it interact with like turbulent heat fluxes calculations at all?
No. They do, I mean, they drain to the ocean so you can get, or they drain so you can get like fresh water into the ocean, but no impact on the turbulent heat fluxes and stuff.
Thank you.
I had a question about the flow size distribution work. So what kinds of observations would be useful beyond flow size distribution, like flow shape or?
I mean, we're not resolving shape. So I think it's more just like the areal size, looking at longer term observations of PDFs, do those change in time or space, and being able to assess it that way. So like, looking at the seasonal cycles of some of those things, or maybe changes in time. I don't know everything that's available in the observations. And I would definitely say, I wish I could remember if it was this week or next week, but yeah, this meeting that's happening in Brown, it's this week. Yeah, because everything overlaps. I know they'll be talking about that sort of thing more directly as well, and like what's available, but I think that's been one of the challenges is like, with sea ice area, we can compare to long-term passive microwave or something like that, and with like a flow size, we're like, okay, how do we know that we're getting this right other than qualitatively? Like I said, it looks like in the pack we have bigger flows. Are they the right size exactly? We're not sure. Like, is it transitioning correctly through the marginal ice zone? So I think those different types of ice would be valuable too.
Okay, yeah. Asking because we've done a lot of flow size distribution analysis on MODIS data, so it's like really much lower resolution, but we do have it for 2 decades over the visible time period.
Yeah, so, I think that could be really valuable and helpful. Even if it's lower resolution, maybe it has known limits to the smallest flows that maybe within the model, we can look at really small flows that it wouldn't be observing, but I think that would be a great baseline too.
Okay.
Yeah.
Yeah, this is a very nice talk. Can you tell me more about how the NCAR group developed CSM3 or other model? It seems like each group working on their own module and assemble together. And if there is something error occurs, how did you manage? How did you just deal with that type of like a bias? And it seems like from your first slide, it seems like this small, not small, just like one parameter, you can change a lot. So. Yeah. Why you guys didn't get it done in the beginning, but after release, few years, and so how?
So like a coupled Earth system model requires, hundreds of people ultimately to be doing this. And so one of the challenges sometimes in the Arctic, and so for like CESM2, is that the way we developed CESM2, we got to a point where it was like producing a semi-reasonable historical period and stuff like that. And it was like, okay, the model's frozen. And we were like, wait, we want to tune the sea ice. And they were like, no. So for those simulations, like the CMIP and the large ensemble, it's not tuned, but we have some simulations that we've done in the Polar Climate Working Group. I think we have now like 10 ensembles where we did this tuned ice albedo. We showed that the polar climate in the Arctic looked better and that there were pretty much no statistically significant differences in the rest of the globe. So like, hindsight, yeah, maybe we should have pushed harder for that, but we didn't have that data yet, and some of it's just compromising. You're trying to make sure that the whole Earth looks reasonable. We're kind of running into that again with CESM3. We started trying to put the model together, like over a year ago, and you always run into things where the groups do their own little like things that they're changing, and we're trying to do a better job of like, as a group changes, we come back and like build a model and then go back and do stuff so that it's not just like do your own things and then throw it all together at the end. There's always challenges that come up with that too, and developing intuition about a new system. So for like CESM3, for example, one of the things we're finding is that like the Antarctic sea ice has been far too extensive, and we're trying to figure out why. And I think it has to do, it's probably a coupled problem about where the jet is in the southern hemisphere, but also has to do with the ocean and mixing and then how those things interact. And so it's not a simple process to get an Earth system that looks correct, and you have to kind of make, make compromises along the way about what you'll do. So that's part of why CESM3, I was kind of like alluding to, it's been delayed, and it's partly because as you bring those things together, different issues come up because people have been testing in these, like you might test the sea ice in a coupled ice-ocean framework where you're forcing it with the atmosphere, but the atmosphere doesn't respond to it. And then once you get it into this coupled system, you get a weird feedback that you're not expecting, and you have to address that and figure out why you're getting that. The same thing happens with the atmosphere or land models. They change something, they've done this in like prescribed SST runs, and then all of a sudden that's impacting the whole, like, the sea ice, and we're like, wait, let's try to figure it out. And it just takes a long time to actually figure it out. I think some of the challenges with that are just people time and software engineering time. Like, it's not sexy, and foundations don't want to be like, yes, we will support ongoing model development and maintenance. So it would probably be helpful if people had more time and there were more software engineers to help address some of these things. I don't really know how to solve that problem. I'm not paid enough to figure that out.
Thanks, Alice. I'm really into, I think that the large-scale drift of the sea ice is a really important thing, and I'm really coming to appreciate it more now. And so I was curious if you could comment on how the large-scale drift in the model is, how well it represents observations or what we think the real world is, and is that changes in lead sizes, is that influencing that large-scale circulation of the drift?
But do you mean, like, does it replicate like the observed like Beaufort High and transpolar drift? So it has a good mean state. I think we know that there are some biases in the ice speed. So mentioning like we don't have form drag and stuff like that. So that's something that could definitely be investigated in the future. I don't know that I've seen any really good studies about like changes, because I know sea ice is supposed to have been getting faster over time. I don't know that I've seen that within any studies about that within the model. So that's probably something to investigate. Yeah. All right.
One more minute. I don't have to.
Sure.
You were talking about
machine learning parameterizations, and we have a lot of folks who are involved in model development here at centers. I'm curious whether you or others at NCAR are sort of thinking about like how ML-based approaches, and which we're going to hear about in the next session, can coexist inside existing code bases that might not have the libraries to play well with those. So I would imagine in CESM that might be an issue with legacy code.
Yeah, so at least for the sea ice so far, the machine learning we've done is to like guide development and enhancements. It's not run online while we're running the models. I think other parts of the model are trying to use that, but I'm less familiar with that. I guess my personal thoughts on the machine learning are that it's like a really valuable tool but can be used like in tandem with the dynamical modeling. It shouldn't be used to replace all of it. I mean, if we don't have models with processes that are sensible or reasonable output, then you're training your machine learning model on crap. So we can't just like get rid of the model and just use those. I think it is really valuable for understanding the data and being able to like look at parameter space and I know they do that in the land model a lot, is look at parameter space within these machine learning frameworks. But yeah, I don't know about running it online at the same time at this time. So it's like, I think of machine learning as like a really valuable tool to enhance our understanding of the data we have, or to maybe help us make the model, like you have machine learning informed parameterizations, but maybe not actively online. And then like I said too, like once you have several ensembles, you could expand your ensemble size using machine learning with these emulators, but not that it's like going to replace everything or get rid of physical parameterizations entirely or anything like that.
Great. All right. Thanks, Alice.
Yeah.
All right.